Statics, type 7, horizontally suspended. So we tend to see this question come up a lot more on the ordinary level paper than on the higher level paper, but it's a nice question to attempt if it comes up on the higher level. So what we have here in 2009 is a uniform rod of length 2 meters and a mass of 34 kilograms, and it's suspended by 2 vertical strings. So we don't need to resolve those strings. So one string is attached at a point 20 centimetres from one end and can just support a mass of 17 kilograms without breaking. And the second string is attached 30 centimetres from the other end and can support a mass of 20.74 kilograms without breaking. So they are basically representing the upward forces. So the maximum upward force that it can apply is going to be mass times gravity, in other words, 17g. If we're looking then at the mass that is attached to the rod, so it's going to be hanging from the rod, it is a mass of 3.4 kilograms. And basically it can be attached anywhere between A and B. And that's what we're looking for. What is the length of the distance between A and B, so that we can attach this 3.4 kilogram mass without breaking the string. Okay, so let's draw a nice diagram here and label in all our forces and our distances and the information given to us. Okay, so we're going to have an upward force. Let's call it T. And that is a distance of 0.2 of a metre. So we want to change from centimetres to metres there. We have the weight of the rod is going to be at the centre of gravity. And obviously the rod length is 2 metres, so therefore that would be 1 metre to either end. And we have another upward force. I'll just call it F. And that's a distance of 30 centimetres from the end, so in other words 0.3 of a metre. And then what we have is our mass is going to be attached. So let's call it, and this mass has a mass of 3.4 kilograms. So its weight then will be 3.4 g. So if I look at its position, let's say its position A, then from the upward force T, we'll call it a distance of x. So I'm going to say let x equal the distance of the mass to T. Okay, so what we want to do is work out what is the first possible position this can be from T, where our T is supporting a mass of 17 kilograms, so therefore that's going to be 17g, because weight is mass times gravity. And F can support 20.74 of a kilogram, so its upward force must be 20.74 grams, and the weight of the rod itself is 34 kilograms. So therefore that's going to be 34g. So mass times gravity there for each of those. So to work out our unknown here, what we're going to do is look at our law of coplanar forces, and we're going to go with our clockwise and our anti-clockwise moments because we're looking for the perpendicular distance. So our moment is our force multiplied by our perpendicular distance. So the sum of our clockwise moments equals the sum of our anti-clockwise moments around any fulcrum. So what we're going to do is we're going to choose our fulcrum, And I'm going to choose the fulcrum to be the upward force T. So we're going to take our fulcrum at T. So that means that's going to eliminate that upward force at T. So therefore, if we're looking at this diagram, we're going to need to figure out which is the clockwise, which is the anti-clockwise moments. So I'm going to star my fulcrum here. So my fulcrum is at T. So that means I have this downward force here, 3.4 grams, and that's going to make that turn in a clockwise direction. So that's going to be a clockwise moment, as will the weight of the rod itself. And then F is going to pull it in the opposite direction, which is an anti-clockwise moment. So therefore, we're also going to need to know what is the perpendicular distance from F to T. So I know that F from the end is 0.3, and I know T from the end is 0.2. So therefore, the distance between T and F must be the rod minus 0.3 and minus 0.2. So in other words, the distance from T to F has to be 1.5 of a meter. So in other words, 0.2 plus 1.5 plus 0.3 is 2 meters in length, which is the length of the rod. So therefore, we can say, well, our clockwise moments must be the force, which is the weight, times the perpendicular distance, and the weight, which is the weight of the rod, we said was 34g, times the perpendicular distance. So the perpendicular distance from the weight to T has to be 1 minus 0.2. In other words, it has to be 0.8 of a meter, because 0.2 plus 0.8 is 1, which is the halfway position along the rod. In other words, the centre of gravity of the rod. So therefore, that's going to be 0.8. And that must equal our anti-clockwise moments, which is the force F. So that's going to be 20.74 G, so mass times gravity, times the perpendicular distance from F to T, which we said there was 1.5. So that makes it just basically a linear equation now to get x on its own. So if we simplify that, we have 3.4 G times x plus 27.2 times G, and that's equal to 31.11 G. So bringing everything to one side and getting x on its own, we have 3.91 G, and obviously I can divide across by G there, and then divide across by 3.4. So that gives me x is equal to 1.15. And that's of a meter. So in other words, the distance from the 3.4 kilogram mass to the upward force T is a distance of 1.15. So now we need to look at, well, what's the second position it could be at? So in other words, position at B. And therefore, we need to look at taking our clockwise moment somewhere else. So I'm going to take the clockwise moment, I'm going to take the fulcrum, I should say, at the other upward force, which is at F. So we can eliminate F. Now you could take it at W as well. You can take it anywhere you want. So I'm just going to take it at the other upward force. So again, we have our upward force is fixed at 0.2 meters from one end and 0.3 meters from the other end, and the weight again at the centre of gravity. So what happens if we look at the second possible position that this 3.4 mass can be at? So again, 3.4 G is its downward force. And again, I'm going to stick with getting the distance from T. And this time we're going to take our fulcrum at F. So we can take our fulcrums wherever we want. Okay, so if I'm taking at F, well, we need to look at what are going to be our perpendicular distances for each of these forces and which ones are going to be clockwise and anti-clockwise. Okay, so, if I look at the weight is going to be a distance to F of 0.7 meters, because again F is 0.3 meters from one end, 1 meter is halfway across at the centre of gravity, so therefore from the weight to F it's going to be 0.7 of a meter, and that's going to pull it in an anti-clockwise direction. 3.4 g is also going to be in an anti-clockwise direction, and its distance to F is going to be 2 meters, taking away 0.2, taking away x and taking away 0.3, which is 1.5 minus x. And then t is going to pull it in a clockwise direction. That'll cause a clockwise moment. And the distance between t and f we already know from the previous is going to be 1.5. Okay, so now we have each of our forces and their perpendicular distances. Well, we can say the clockwise moment must be equal to the anti-clockwise moment. And our clockwise moment is this upward force T, which we said has a mass of 17g, a weight of 17g I should say, times the perpendicular distance, which is 1.5. And that must equal the anti-clockwise moments, so that's going to be 3.4g times the perpendicular distance, which is 1.5 minus x, plus the weight, which is 34g, times the perpendicular distance, which is 0.7. So again, multiplying out our brackets and simplifying, we have 25.5g is equal to 5.1g minus 3.4gx plus 23.8g. So bringing everything to one side then, we have 3.4gx equals, which gives us 3.4g, and of course if I can divide across I can cancel my g's there, and 3.4 goes into 3.4 once. So that means the distance from the mass to t is 1. So now we have basically two different values. So we have the distance from the mass to t is 1.5, and the distance from the mass to t is 1 meters. So therefore that means that the distance from A to B has to be the difference between these two positions that cause this rod to be in equilibrium. So in other words, we can say 1.15 minus 1. So in other words, the distance between the two positions that this mass can have to keep it in equilibrium has to be 0.15 of a meter. Okay, so we had 10 marks for working out our first one. So setting up our clockwise and anti-clockwise moments and getting a value for x. And then same again, so second equation and solving for x, and then working out the distance between them. So 25 marks in total. So really, really nice question. So this is a very similar one from 1996.